I think I have only 18 slides or so. So I don't know, it may even end before you think that I should end the lecture. So this is regarding time evolution in quantum mechanics. I particularly chose this topic keeping in view the MSc students and also faculty who often we consider uh, Schrodinger's equation. And what is the first class discussion? There are time independent Schrodinger equation, time dependent Schrodinger equation. This is time independent, this is time dependent. We simply go about mentioning that. I thought, why not we explore this a bit further and try to see what are the different manifestations of time evolution. Oh, I see some more regional college students here. I am teaching them. So, thanks for coming. So, time evolution in quantum mechanics and the quantum Zeno effect. I think you know Zeno paradoxes. There are 3 paradoxes. So, maybe when I come there, I will try to talk about that. Secondly, this is not 2024 physics, right? This is more or less a concept-based lecture. So maybe somewhere I may refer to something which may have slight link with what Professor Umesh is also told this. So there are 3 roads to quantum mechanics. If you want to understand quantum mechanics, there is not just one way. So you can choose any of these 3. So you may hate Schrodinger because people would have in the class made Schrodinger very difficult for you. So then there is Heisenberg and then there is Feynman. So there are 3 roads. It means you can either use Schrodinger's approach or Heisenberg's approach or Feynman's approach. So what does Schrodinger say? So let us understand the problem. The problem in physics is we give a system. We have a system in front of us. And the system has certain description now. And after some time, because the system may be influenced by other interaction, the system will acquire another configuration later. So the question in physics is, how does the system evolve from this initial state to that final state? This is the only problem more or less in physics. Newton did it. He gave his equations of motion. So, but the domain of application was less. Therefore, we went beyond Newton. Quantum mechanics came. Even in quantum mechanics, the problem is same. So, here is an initial situation of the system. What is the purpose? What after some time it will achieve some other manifestation. How do I understand that? How do I find it out? So Schrodinger has an approach. He says that start with psi of 0. Psi of 0 is the initial state. Don't ask quantum mechanics, give me the initial state. No. You see, quantum mechanics, it is like a doctor. You have to go and tell what your problem is first of all. He will give prescribe medicines for you. So you have to tell the Schrodinger, you have to tell him that this is my initial state. And then he will ask, what is the interaction? So that is given here in h of t. The Hamiltonian will contain the interaction. And Schrodinger says, give me psi of 0 and then give me h of t, then solve my equation. This is the equation which you have to solve. This is a differential equation for psi of t. So what is meant by solving? What is psi of t given psi of t naught under this? So you go to mathematics and use the techniques of mathematics and find out the solution. That is Schrodinger's way of doing it. By that, let me also tell you 2 more things, that according to Schrodinger, the system, the manifestation of the system is through the waveform or the state. He says that as the system interacts with anything, this state evolves in time. So what was psi of 0 will become psi of t later. How do I measure anything that I want? Do you want momentum? Do you want position? Do you want to know what is the energy? There are operators for them, according to Schrodinger. These operators, they are, static. They don't change with time. So take the Hamiltonian operator, apply it to psi of t, you get the energy at time t. Take the same operator, apply it to psi of 0, you get the initial energy. So the initial or the final value of the operator are obtained by applying the same operator but to the initial states and final state. So this is the method according to Schrodinger. Heisenberg has another approach. He says that for me also you have to give the initial state. So once you give the initial state, he says that I give you an equation for the operator, not for the state. He says that the physical system is represented by certain configuration, psi of 0. It will be there. As it interacts with other influences, the properties will change. The properties are represented by operator. Therefore, according to Heisenberg, the operators change in time. So, how does the operator change in time? If Schrodinger gives an equation for state, Heisenberg says, I will give an equation for the operator itself. So, this is the Heisenberg's equation for operators. Of course, Heisenberg won't call them as operators, he called them as matrices. It was such a nice observation. I don't know, how this quantum jump came. Schrodinger came with operators. Heisenberg did not know about matrices, it seems. And later he went to the library. Unfortunately, the library was closed on that day. So he was waiting like anything till next morning the library to be open and all. But anyway, we often resort to Schrodinger's formalism. This is more because, let me share with you, you know that in linear algebra, if you have an operator, then it acts on a vector space. With respect to a basis, it will assume a matrix form. That means there will be a matrix corresponding to the operator. Suppose you change the basis, the matrix form will change. Essentially, Schrodinger's formalism is like working with operators themselves. Heisenberg's formalism is like working with the matrices. So essentially there is a correspondence between the two. Perhaps why Schrodinger's mechanics or quantum mechanics became more popular is because with respect to Heisenberg's mechanism, you have to stick to a basis because it is basis dependent matrix. If you change the basis, the matrix will change, but the operator remains. So it is basis independent description. Dirac went one step even further. So he gave his bracket formalism. In Schrodinger's representation, you have what is called position representation, momentum representation, and all that. So even Schrodinger's representation is not all that independent of this representation. Dirac's method is one representation. However, this is the difference between Schrodinger and Heisenberg. Although these two gave the description of quantum mechanics, there are certain fundamental issues on the philosophical aspect, foundational aspect with respect to Schrodinger's or this quantum mechanical description given by both of them. So people, even the last word has not been told yet. In fact, you may be knowing this, that I often, take pleasure in telling this. When Einstein gave his special theory of relativity, the whole world did not understand for quite some time, right? But Einstein was right. He published it. But when the entire world produced quantum mechanics, Einstein stood against it, right? He said, I am not happy with quantum. In spite of contributing something to quantum mechanics, right? That is something great about Einstein. So there are some fundamental or foundational issues. For example, entanglement that Professor Umesh was telling, and even Dr. Usha Devi might have told, the realism assumption of Einstein. He did not like quantum mechanics because of the realism assumption. However, less problematic and more supporting is the Feynman's approach to quantum mechanics. He says that he looks at the positional description only. That means give me psi at x naught and t naught, and I will give you psi at x and t. How do I give it? I will. Here is the initial situation. Here is the final situation. I will consider all possible paths that can connect this and this, and I will consider every path along with its contribution, and that is that integral. So I have given a simplistic view. So if you just do this integral, you will get psi of xt. Of course, this method is not so easy to understand. Perhaps that is one reason why it does not come into our post-graduation discussion. I don't know. I mean, whether.
Hardly also discuss this.
Oh, that is nice then. Right. So these are the three roads to quantum mechanics. However, could be right. So let me come to this time-dependent Schrodinger formula. So I would like you to, just pay attention to something that I would like to tell here. First, I am going to consider time-independent Schrodinger formula. What do I mean by time-independent formalism? I have the same Schrodinger equation. H of t is given by p square by 2m plus v of t, right, in general. If v is independent of time, so will be h. Then we say that this problem is time independent. So what do we do? How do you solve this equation? Look at the first equation. IH cross d by dt of psi of t is equal to h psi of t. You can write it as, using the definition of the derivative, for small epsilon, this is psi of t naught plus epsilon minus psi of t naught divided by epsilon is d psi by dt, right? So I am using that, I am sending that epsilon to the other side. Using that equation, psi of t naught plus epsilon minus psi of t naught is equal to this quantity. This h no longer time dependent, it acts on psi of t. So this psi of t naught plus epsilon. So that means the state at time t naught plus epsilon is related to psi at t naught through this. What is psi of t naught plus 2 epsilon? Simple, it is 1 minus the same thing acting on psi at t naught plus epsilon. Whatever applies to t naught and t naught plus epsilon applies to t naught plus epsilon and t naught plus 2 epsilon. So, but you can once again express this using this. This becomes 1 minus I epsilon by h cross h whole square psi of t naught. Suppose you break up that entire t into t naught plus n epsilon. So psi of t will be this to the power n, and that is the e power minus I h cross t minus t naught h psi of t naught as n tends to infinite. This is the form that we write.
You said h of t will be time independent if v of t is time independent.
Yes.
So that implies that p or p square is never time dependent.
In Schrodinger quantum mechanics, no. It is momentum operator is momentum always. Only if you are doing Heisenberg operator, he will say P itself goes on changing. The state remains as it is, the operator changes. So that idea is simple. You are taking expectation value. Psi of t, operator, psi of t. That is the average value. What you can do is remove this, write this psi of t as e power minus psi h t into psi of t naught. Here also you do it. So what you get? Psi of t naught e to the power of plus psi h by t into operator into e power minus h. You call this quantity as the developed operator. Initial state developed operator or operator developed state. So both are same. So here I am doing in Schrodinger quantum mechanics. So this is how I get this. So I have written again. If you consider this form, suppose as an Hermitian operator, Hamiltonian has got eigenstates. So let us say the eigenstates of this Hamiltonian are psi k, which have energy ek. So such that they are orthonormal. So h psi k is equal to ek psi k. Then these are eigenstates of the Hamiltonian. Suppose the system at time t naught Well, it may be in one of the eigenstate or it may be in several eigenstates, so that is a linear combination. If that is the case, then psi of t can be easily worked out to be this. So which you do in the class, right? So how to solve the time independent problem? Just solve this equation, h psi k equals e k psi k. So if you have Schrodinger's time independent equation, the only problem that you have to do is to solve the eigenvalue problem. You have done it for harmonic oscillator, hydrogen atom, rigid rotator, one-dimensional potential well. So all those are time independent problems. So our job just reduces to solving that equation. Once you solve that equation, you have the general solution given by this blue equation. So what does it say is one thing more. Initially, if the system was in certain linear combination, then finally these CK coefficients will have something more. So the linear combination changes, but the individual probabilities remain same. That means mod, if you take mod square of this, since this is exponential, it will go away. So mod CK square, whatever was the initial composition of each eigenstate, that composition, that probability remains same.
So I think you are assuming if we have to use that red equation, then by assumption, psi k time variation is e to the power of minus I omega t also.
Psi?
The time variation will be like e to the power of I omega t, so that IH cross delta by delta t gets.
These psi k's are they no longer have any time dependence. These are eigenstate of H. Psi of t naught, psi of t, they have the time dependence.
If I start from time dependent Schrodinger equation.
Time
dependent. And then I say time dependence is harmonic e to the power I omega t.
You mean what is changing harmonically?
Psi is some psi a e to the power of I omega
t. You are considering time dependent equation.
It is time dependent.
Please wait. I will. That is my next thing. So there is some problem with time dependent Schrodinger equation. So thank you for giving me a reason to show this slide, because this is a consequence of your question, right? So time dependent Schrodinger equation. What is the problem here? Here V is a function of time. So IH cross d psi t by is the same equation. Equation is same. H is time dependent. So we can write psi of t as some unitary operator acting on psi of t naught. But what is this unitary operator? It is given by something like this t of this thing. I don't think we tell this in the class. I don't know whether Chuling Swami may be also teaching. In the case of time dependent Schrodinger equation, the time evolution, initially the wave function is given by this. The final wave function is not just e power minus I h cross t, that it does not come out of the integral because itself is time dependent. So what is meant by this time? This is called time ordered integral of this. So once the equation is time dependent, you cannot use e power minus I h t by h cross. You will have to use this time ordering. What is this time ordering? I am using the same idea. Again, dip psi by dt is this one. For small epsilon, psi of t naught plus epsilon is as before minus psi epsilon by h cross h of t naught psi of t naught. Or in other words, psi of t naught plus epsilon is 1 minus psi epsilon by h cross h of t naught psi t naught. Earlier there was no t naught at all because h was time independent. Now let us go to psi of t naught plus 2 epsilon. So this is 1 minus I epsilon by h cross h of t naught plus epsilon acting on psi of t naught plus epsilon. So if I write psi of t naught plus epsilon, it is 1 minus I epsilon by h cross h of t naught psi of t naught. This is h of t naught plus epsilon. This is h of t naught. The Hamiltonian at time t naught and the Hamiltonian at time t naught plus epsilon. These do not commute in general. Therefore, if I want to consider after a long time t, which is t naught plus n epsilon, I have to write 1 minus I epsilon by h cross h of t naught plus n minus 1 epsilon. Go on like this and finally come to h of t naught and psi t naught. This first I have to do Hamiltonian of t naught acting on psi naught. Then I have to do this acting on t naught. So I will have to act on psi naught by this time ordered Hamiltonian, that is. So this entire expression is written as this. So that is the meaning of time ordered integral in time dependent Schrodinger. Okay, so that is for any general time dependent. Let me consider a special case called the adiabatic change in time or slow variation. That means I have a Hamiltonian which does not, suddenly it is not switched on like this switch. To switch off, I mean, off condition there is no light, on condition there is light. So this is a sudden change. Suppose I have an interaction in which the Hamiltonian is changing in time. So the Hamiltonian is changing very slowly. So you may accept when I say very slowly, but if you ask me, can you tell me how slowly it is? Because what is slow to me may not be slow to you, right? So there must be a reference for which saying that compared to this is slow. Otherwise it is meaningless. One man's food is another man's poison, they say. So in fact our teacher was telling, maybe our students know it, but there are some new students here. So let me share that with you. Just to pay. Professor A.V. Gopal was such a nice teacher who taught us. So he said one day he came and sufficiently small, he was telling. So then do you know it is meaningless if you just say sufficiently small? He said, right. So we of course did not know. Maybe he said that one professor one day was teaching in a class and he asked some student about how many ties, neck ties are needed to connect Earth and Moon. The question was actually what is the distance between Earth and Moon, but the professor wanted to twist it and he seems to ask how many ties are needed to connect Earth and Moon. One smart student stood up and said, only one tie is enough if it is sufficiently longer. So what is relative may not be very. Yeah. Anyway, right. So when I say slow variation, let me also not make the mistake of just saying that there are two Schrodinger equation in time independent problems are, we write e power minus iet by h cross. That gives one kind of time variation. Compared to that time variation, if the Hamiltonian varies slowly, then something happens. What is that something? So h of t changes slowly in time. The Hamiltonian may appear constant over an infinitesimal interval in time. So it is such a slow thing. Maybe you have applied a magnetic field. Today it is some 5 Gauss or something. Like tomorrow it will become 5.1 or something. So such a small variation is there. Then you can, for that interval of time, h appears to be constant. Whenever there is h operator h, you can construct eigenstates for h. So this phi of t is an eigenstate of h with eigenvalue e of t. So you can mathematically construct that given the Hamiltonian. So phi of t satisfies normalization. What is this phi of t? What name shall we give it? So t is varying. So there is phi of t naught also, phi of t1 also, phi of t2 also. So anytime you suggest there is a phi of t. So these are called instantaneous eigenstates of the Hamiltonian. Is it a solution of the Schrodinger equation? That is a different thing. This psi of t which occurs in the Schrodinger's equation satisfies a differential equation. Phi of t satisfies this eigenvalue equation. So there need not be any relation. Nobody can check. Suppose the solution of Schrodinger's equation may turn out to be an eigenstate at time t. That is also a possibility. So suppose psi of t is something into phi of t. Suppose, let us say, that which we don't know. So since we don't know, we can't call it a solution. Suppose we substitute this into the equation and try to find out these values, then this psi of t will be a solution under the conditions guided by the equation. So if I substitute this into the Schrodinger equation, then this quantity, this is called the dynamical phase. I told you the variation in the energy. This C of t, which is unknown, will become C dot t phi of t. That satisfies minus C of t into phi dot of t. So this phi dot is d phi by dt. So told in another language, if psi wants to be phi of t, then written in this form, it can be solution of the Schrodinger equation provided the C of t satisfies this condition. So if I can solve for it,
the propagation in homogeneity. There is something called the WKB approximation. Can that be tried for the time, the slow time variation?
In WKB approximation, I think that it is not time dependence. The change is not due to time dependence, right?
Well, mathematically, I have just here you have t.
Yeah, but the Schrodinger equation is only for t, right? Oh. So in this equation, in time dependent equation. Okay. So C dot t phi of t is this one. So if you under adiabatic approximation, I will tell you what is that that slow variation. But that slow variation is a qualitative way of telling it. I also quantified it by saying that it is smaller compared to this. But more specifically, what is adiabatic approximation? I will tell you in a minute. But you can write this as the solution. C of t is C of 0 exponential I gamma t. So this gamma t is given by this expression. So this psi of t becomes a solution of Schrodinger equation provided C of t satisfies this, which means psi of t will be some C of 0 e power I theta, this is the dynamical phase, into some additional phase. This additional phase, I think there are MSc students here, perhaps. This is the Berry's phase that we teach in our quantum mechanics class. Incidentally, that is, if there is time dependent Schrodinger equation and if you solve using this eigenstate, the wave function develops an additional phase or a phase in addition to dynamical phase, and this is called Berry's phase. Well, I told the sentence earlier and I am repeating it. The reason is, I must tell you that there was an Indian who had shown this 30 years prior to Berry. And his name was...
And he was in this department.
I think he gave the punchline, right? So he worked out, his name is Pancharatnam. He was a faculty in this department. So I think that speaks of being so young, he was so ahead of in quantum mechanics. So in fact, when people brought this to the notice of M.A. Berry, Berry said, had I knew that Pancharatnam had done this, I would have written my paper in a different way, giving proper acknowledgement to Pancharatnam. So anyway, so...
But it is still called the Pancharatnam phase.
Of course. Let me, now that Professor Umesh has said it, what Pancharatnam did was in the case of light only. What Berry did applies to any general quantum system. The idea is same, but Pancharatnam had done it only in the case of given two beams of light. And suppose, what is the condition, under what condition I should say, I could be able to say that this and this beam have the same phase, right? They interfere constructively. So there is a phase difference. That phase is called the Pancharatnam phase. Its work was in optics. There is a, if you are belonging to an institution, you ask your institution to write a letter to RRI, Raman Research Institute in Bangalore. They have large collection of books, collected works of Pancharatnam. And if you go to RRI, you can even borrow it for a day or two, and you can this one. So if your institution requests, they will send even a copy to your library, and you will see a host of papers, right? So anyway, coming back. So if initially psi of 0 was phi of 0, then after some time psi of t will be phi of t. So the moral of this is, under adiabatic change of the Hamiltonian, eigenstate follow the Hamiltonian. So they were earlier eigenstate, so they will go behind the Hamiltonian, which means that the eigenstate at time 0 will develop to the eigenstate at time t under adiabatic approximation. So what one thing that I did not tell you is, this adiabatic approximation is an approximation because when in this case, if you consider this, psi of t cannot be written as a single state like this. It has to be written as a linear combination of the eigenstate. But under adiabatic approximation, you can neglect the other terms. So this is one way. So I just wanted to say that eigenstate evolves into eigenstate. Perhaps this agrees with the title of my talk, Time Evolution in Quantum Mechanics. This is how a state develops. You may
basically some phase factors get added.
Yes, provided that adiabatic this. Maybe yes, you are right. Right. So one interesting thing is, now that let me mention. Thank you. I thought my lecture would be ending very soon. I was thinking when you were giving lecture, initially I couldn't concentrate for my own biological reasons, right? I was feeling sleepy. But after that, I could get some idea that what feature can I borrow so that I can elongate my, stretch my lecture, so that people won't object that you have given lecture for only 1 hour, but you are supposed to give 1.5 hours, and your money will be cut off and everything. So that is, this additional phase can be used in the case of light. Experiment was done. Simon and others from Chennai showed that you can change the frequency of laser light slightly, to some extent. You also were saying that some smaller change or a narrow change in frequency can be done using some new idea. So same thing can be done using this. So a quantum idea also practically allows you to change the frequency of light. So eigenstates evolves into eigenstate. So the opposite thing is sudden change. So suddenly apply a strong magnetic field. Initially the system is in an eigenstate, and you suddenly apply a new magnetic field. So earlier it was H0, now it is H dash C. So what will happen to the eigenstate? It seems the eigenstates will be sleeping. It will continue to be in the original eigenstate. It cannot feel the quick arrival or onslaught of the new Hamiltonian. Maybe you can read that in your quantum mechanics book. So let me also go to another time-dependent situation. I have an interaction. A system is interacting with another maybe magnetic field or electric field. So H is dependent on time. The first one is the Schrodinger equation, where H of t is the Hamiltonian. What I will do is, I will change my psi. I would like to write a new psi dash. So why do you like you, Messiah? Give me some freedom. What is there? I will write psi is unknown. I will put another unknown. So psi dash is something into psi of t. That is this. Psi dash t is u of t, psi of t. So have I solved it? No. If I find psi of t, then I can find psi of t. My purpose is to find psi of t only. So for which you may ask me, why are you doing this? So please be patient. Why I am doing is this because I would like to write a Schrodinger-like equation for psi dash of t. You may ask me, why do you want to do it? So there is some purpose. So if I write psi dash equals u of psi, where u is unitary, then psi will be equal to u dagger psi dash. So if I consider IH cross d by d of psi dash, then I have to differentiate both. So it will be IH cross u dot psi plus IH cross u d by dt of psi. Now for this psi, I will put this one, u dagger here. This one is given by first equation h, and then again psi of t. So I will get an equation for psi dash. IH cross d by dt psi dash of t is equal to h prime of t psi dash of t, which means I have a new Schrodinger equation. You may laugh at me. What is the you asked me to solve original Schrodinger equation, and you are developing some psi dash. What is the purpose here? Now the purpose is the following thing. What is my h dash of t? It is IH cross u dot u dagger plus ut h t u dagger. My h is time dependent. My u is time dependent. Now h dash is this. Now I will meddle with u. I will use the time dependence in u and the time dependence h and try to see whether this whole thing can become time independent. Right? If this whole thing becomes time independent, my equation becomes time independent Schrodinger equation. So I can solve using time. I will find psi prime of t. And what is psi of t? Simply u dagger of t psi of t. So I can solve the original Schrodinger equation with this method by changing the time dependent problem into a time independent problem. So h prime t may be time independent. So that is the hope. Everything will not come to you on a plate, right? You just whatever you ask for. So it may not be true. I will give you an example. Suppose, consider you are at the center of a circle and there are two of your friends. One is moving around in the clockwise direction and the another one is moving in the anti-clockwise direction in the same circle. So if somebody comes and asks you, is there any time dependent thing going on? You will say, yes, here is my friend running around, in time. And the other friend is running around in this time. So can you reduce this time dependence somehow? Yes, you can do in the following way. What you do is, suppose you start rotating with one of them, then that person will be at rest with respect to you. But the other person he will still be rotating, not just still be rotating, he will be rotating with twice the frequency, right? Earlier he was going like this, now he will be going faster. And what is the outcome of this? In physics, in interaction, if something goes slow, that can cause some interaction, right? If something goes very, very fast, then there may not be time to see any interaction at all. I am not at all referring to every situation. Maybe you can consider nuclear fission itself. When the neutron goes slowly into the nucleus, fission can occur. But if the neutron goes faster, it will simply go, the cross section will be. So similar to that, in this situation, if that which is going faster has negligible average, its average effect is negligible because of its fastness. So what I mean to say, if you are in a frame and if you go to a new frame, a rotating frame, in the rotating frame, something which was earlier totally time dependent will become at least time independent to certain extent. So consider certain nucleus. This nucleus will have nuclear level. They will all have the same energy. Apply a strong magnetic field, constant magnetic field. They will separate like this. So the magnetic fields levels are separated. Then start sending an oscillating magnetic field. How do you get that oscillating magnetic field? drive an AC current through neuron, this one setup, artificial electromagnet. Then this current is I naught cos omega t, and the magnetic field will also be cos omega t. And this cos omega t can be written as e power I omega t plus e power minus I omega t by this e power I omega t is nothing but clockwise rotating thing. E power minus I omega t is the anti-clockwise. So in your frame, you have applied a constant magnetic field. In addition, you have applied a radio frequency field. If you go to the new frame, that means if you start rotating, then what happens is one component will remain constant, the other component will be going around very, very fast. You can neglect that. And by that, you have made in the new frame, things have become time independent. This is called rotating wave approximation in nuclear magnetic resonance. That is the picture that is written here. Here is the sample, here is the magnet, here comes the RF signal, and when the frequency matches, you get a signal. So this is theoretically analyzed by this rotating wave approximation. So this is another way in which you can handle time dependent phenomena. So then this is another thing that I wanted to tell. This title also I thought I should use what Professor Umesh was telling. So what is this? This is called coherent superposition. What is meant by coherent superposition? You have atoms. Atoms exist in various states. What you do is you try to prepare the atoms or each atom not in one state, not in any other excited state, but in a linear superposition of any two states. So this is called coherent superposition. If you can achieve this, then such a mechanism helps you to achieve something like this, the following thing. Coherent superposition of atomic state leads to coherent trapping. Lasing without inversion. This may look surprised. Lasing without inversion. Inversion, our teachers have told, dear student, even if you forget to write anything, first write population inversion should be there for lasing, right? But here is a mechanism which says that there can be lasing without population inversion, and the other way also, inversion without lasing, and self-induced transparency. And there were more I thought to include, but as it goes, maybe some slide has some more details. Coherent trapping is the following thing. Excited state population remains constant, right? Suppose you take here a structure, here is a level C, here is a level B, here is a level A. Now, you drive this A and B with an electromagnetic field like Professor Umesh was telling, so you send some electromagnetic field which couples A and B, dipole coupling. Similarly, it can couple to another C, right, level C, under dipole coupling only. Right? Between these two, so I think if this has dipole coupling with this has dipole coupling with this, then between these two there can't be dipole coupling. I think because delta L should be 1 here, delta L1 should be 1 here. Between these two, that won't be satisfied. So there won't be the dipole coupling. So what you do is you consider an atom with 3 levels in lambda configuration. This is called lambda. Actually, practically, sometimes these two are degenerate level. So they will send some microwave or something like that and separate them. So this looks like the lateral lambda, right? Therefore, this is called lambda configuration. In another case, this will be above and this will be below. That is called the V configuration. In some other cases, they write one above the other. That is called ladder configuration also. So this is the Hamiltonian. Some initial population in A, initial population in B, and initial population in C. Atom is put under 2 electromagnetic field at resonance. So the resonance is here single photon resonance. Both of them are at resonance. That is, there is no detuning. This will not go above or something like. So this is to highlight this coherent trapping. So here is a laser field or electromagnetic field which couples this to this. So this nu 1, h nu 1 is equal to this energy minus this energy. Similarly, h nu 2 is this minus this energy. So these are the two lasers or electromagnetic field, omega 1, omega 2, this phase factors and all that. So this first field connects A and B, second field connects A and C. So and this Hamiltonian is Hermitian, therefore you add an Hermitian conjugate. This is the interaction part, that is the free part, earlier part. So now solve this equation. IH cross d by dt psi of t. The Hamiltonian now is h naught plus h1 of t psi of t. Let us write psi of t as some Ca of t plus Cb of t, this one Cc of t, like this. So substitution gives you these three equations for Ca, Cb and Cc. Ca dot, Cb dot, Cc dot. What does Ca represent? Later, if you take mod Ca square, that gives you the population of the level A. Similarly, mod Cb square, mod C square. Now, under the resonance condition, now what I do is, initially I chose psi of 0 to be cos theta by 2 into B plus sin theta by 2 into e power minus I chi into C, which means I am choosing initially the population is only in B and C. It is not in A, as you can see. So amplitude Ca of t later becomes something like this. That means after some time you have this. So there will be population in the level A. That is because the fields are acting. So they will pump these atoms to upper level, right? So this can go up and this can also go up, and there could also be downward transition. Stimulated absorption as well as emission may take place, because of which at time t this will be Ca of t. But the choice omega 1 equal to omega 2, theta equals pi by 2, phi 1 minus phi 2 minus chi equals plus or minus phi will make Ca of t 0 for all future time. That means Cb will be 1 by root 2, Cc will also be magnitude wise 1 by root 2. State A has no population initially. Finally also it will not have any population, which means under this condition population is trapped in the lower states only. You say, what is surprising about this? See, you are sending light such that this light will certainly take this here, this will take this here. So there is interaction, there is somebody is pulling you to go up, but you are not going up. That is the situation. That is why it is called population trapping, coherent trapping in lower state. So there is no absorption, even though there are two fields which are existing. So coherent superposition of atomic states leads also to, as I told you, lasing without inversion. It seems first achieve this situation, no absorption to higher state. Then to the same cavity, it seems, I am not very sure, you pump in the same atoms, but now in the excited state. So A. So it is something like in the lower state there are 8 atoms, but in upper state there are no atoms. Now pump in some 5 or 6 atoms. So there is no population inversion, but they have gone there. They say that now, though the upper state population is 5 or 6, but the lower state population is more than that, still now the transitions can occur. So that is what they say as lasing without inversion. I was not very sure, frankly speaking. Since I was not very sure, I did not make a slide out of it. Right? Those of you, please go into this literature, and if you can understand, one day you can talk about it. Inversion without lasing, self-induced transparency. This is also interesting, sir. It seems that under some particular condition, see, when light is sent, the material or something is opaque to light, but at certain particular condition it will simply allow light as if it is a transparent material. So this is called self-induced transparency. And also sometimes its refractive index will change as under certain conditions. So enhanced refractive index. Handley effect is oh, nice. Right. Yeah, I should have. I thought I could have mentioned. Now that you are there, you can help me.
Enhanced refractive index is a E into E into E.
Oh, right.
That E square will act like intensity modification of the refractive.
Oh, right. Thank you, sir. So, Handley effect is you send expolarized light into a system which is prepared in certain way. Somehow you observe polarization of light in some other direction coming along Y or so, something related to that. So, the input and output polarizations are different.
Another thing is, initially at low intensity, the medium may be more or less opaque or highly absorbing.
Yeah. Yeah, observing also.
So if the intensity keeps increasing, it saturates the upper level and this fellow becomes
Oh, nice. So because saturation will not allow further absorption. Oh, now let me come to what is this, my last topic, quantum Zeno paradox. Zeno, you might be knowing, came out with three paradoxes that let me tell you one which is something like, suppose you want to run 200 meters track, you want to run 200 meters race. So according to Zeno, he says that you can never run, you can never complete the race. He says like this, in order to run 200 meters, first you have to run 100 meters. Then still there is 100 meters. In order to complete that 100 meters, you have to run 50 meters. So then you have to run 25 meters, so 12.5 meters. There is always something in front of you. So it will never become zero and therefore you will never complete the race or so. Something. So finally you may even become static or something. But this is some mathematics. People have good explanations. You can also see Zeno's paradoxes as well as solutions using mathematics. However, in quantum mechanics, what is this quantum Zeno paradox? The time evolution of a quantum system, the statement is, the time evolution of a quantum system due to an interaction is going on, which is allowing the system to change as with time. It can change from one state to another. So the time evolution of a quantum system due to an interaction can be slowed down by frequent measurements. So explanation, interaction causes atom in psi b to decay to psi a. Alright. So psi b is the excited state, say, it comes down to psi a. This is an atomic spontaneous transition, right? So it looks like maybe this also one occasion to share with you that we often enjoy, or sometimes we tell that spontaneous emission takes place on its own, right? So if you stop there, then that is against the very basic tenet of science, which says that any effect must have a cause behind. So what is the cause for spontaneous emission? If you say atom simply comes down, right, it looks like there is no reason. So, but the reason is that the electromagnetic field, according to quantum description, exists everywhere. So only thing is, in the second case where there is, you apply an electromagnetic field, the atom comes down giving another radiation, stimulated radiation. Here you are applying an external electromagnetic field. But even if you don't apply any external electromagnetic field, there is some sleeping electromagnetic field. This is also called the ground state of the electromagnetic field, which will always be interacting with the atomic system, and that causes this transition.
That's called same as vacuum state?
Yes, that is the vacuum state. Right, sir. So suppose that time natural width is say tau. That means in time tau it comes down. Here maybe it may come a bit earlier because you are stimulating it. So if tau is the natural time, if you make repeated measurements at intervals of time t far less than tau, you can prevent this transition. So this is quantum Zeno effect.
You said slow down. No, the red statement.
Right. Can be slowed down by frequent measurement, and if that frequency goes to right, it is much frequent, you can even arrest it also. So slow down, I like slow down. Something at rest is also a special case of slow down. Right? So this was first described by George Sudarshan and Baidyanath Mishra. This was done in 1977. Not so old, but a nice concept. So they gave it in 1977. Let me also share with you two things. One is, when we say time evolution of a quantum system due to an interaction, then how does the system evolve? There is a definite equation, that is Schrodinger's equation or Heisenberg's equation. There is an equation which tells you definitely this is how the system changes due to an interaction. But measurement, there is a measurement postulate that is called the reduction postulate. Whenever you make a measurement, a system which was in certain state suddenly changes to certain other state. Is there any equation for that? No, there is no equation. So, when you write reduction postulate, you say that psi b goes to psi a. You don't write something is equal to something there. There is no equation for that. Even today, I mean, the last word has not been told, and still people are trying to see, can we find out some meaning and some expression, some equation for reduction postulate. And certainly it will be a Nobel Prize winning idea, I think. So how to understand this concept? So atom interaction with electromagnetic field, perturbation theory that I had written in the earlier lecture, maybe that was slightly different because this time I copied from another source, so there is some difference, there is an integration and all that. So this is the transition probability per unit time considering all light, etc. For long time interval, say time, that if you consider the limit of this for a long time, then this is proportional to time. This is what we were discussing there also. It is proportional to time. But for very small intervals of time, suppose you consider t is very small, much smaller than tau, say, then PAB of t will be proportional to t square. So it is not just mathematics. For longer time, it will be proportional to that. For a very short interval, this is proportional to t square. So this is the probability of transition from B to A. This is alpha t square. What is the probability of not decaying? Let me call that as PBT. It is 1 minus this probability of decay. So it is 1 minus alpha t square. So there is a system initially. I allow for a time t. So there is a probability of transition. But after end of that t, I go and measure what is the state of the system. Then there is a reduction to certain state. And I will not disturb it till another interval t. So I will go once again after 2t and I will measure. Like this, I go after n intervals of time. So I divide this total time tau to n interval. So the probability turns out to be 1 minus alpha tau by n square whole to the power n. So probability of non-decay is this. If you write that, that becomes 1 minus 1 by n something, 1 by 2, n cube something. I am emphasizing the denominator where n is present. So that if n becomes very large, this becomes 0, this becomes 0, everything apart from the first term becomes 0. So what is the probability of non-decay after long, I mean so many frequent measurements? It is 1, which means it will not decay at all. This non-decay probability expression under n going to infinity becomes 1. This means the system will continue to be in its upper state. Interaction tries to evolve and tries to cause the decay, but intermittent frequent measurements puts the atom back in excited state. So, this is this picture. I just wrote this picture. So there is an observer who is sleeping and the atom is in the excited state at t equals 0, and after tau the observer is not at all looking, still sleeping. So there will be decay in time tau. Right? The next sequence is, here is interaction plus frequent measurement. Here is this observer who is looking at the atom, right? But after observing at t equals 0, is again sleeping there for some small moment. So this continues, and the atom continues to be in the upper. Don't think that it has come down to lower state. I mean, just rotated, that's all. Though it's interaction plus frequent measurement. So a system, if you continue to watch, will not change, right? So suppose maybe this is told as a proverb in English, right? A watched pot never boils, right? So this is a quantum. This is a quantum. This is a truth in quantum mechanics, although it's an idiom in English. So thanks to all of you and to the internet source.
That thing is in a hot plate.
Yeah, right. She has put and she is watching, and it is not. Nothing is happening, right? So thank you all for listening to this. And